all here. Chair, could you please allow me to speak? No, she can't.
Sorry.
I'm just asking if I can start and not be interrupted.
Yes, you can.
Okay, thank you very much, Chair. And thank you very much for the organizers for bringing us all here and making this so intensive workshop that I was really happy, and I have to thank Mateus for losing his flight. So this make me change the last talk of the week for the last talk of the second day. And I'm already tired, and so I hope I can keep alive and enjoying the workshop, and we have many different interesting things to do. And now the chair can know that I will talk about colored graph and
Marcelo Terra Cunha talking about colored graph approach to contextuality and non-locality. Thank you very much.
Great, thank you. And this is not necessary anymore to enforce the importance of contextuality, but this is a foundational. So I would say it's a central issue, it's a central point in non-classicality, in what are the important difference from quantum theory to classical theory. Cauchy-Specker theorem is the central idea of what we are not able to mimic using classical models. And this non-contextual hypothesis is the idea that whatever you do for one question can't change if you do it together with one or other compatible question. This is the central hypothesis. And it was very well succeed, the idea of a graph approach for these things, started by those three guys. It's a long history in the field now, because it was an archive in 2010 that also took long for appearing, because the idea was well discussed in 2009, and it only comes in October. And it only became a paper in 2014, so now we have 2018, and new things can appear also. But the central point is they could realize that in this famous example, the Pentagon, if you sum the probabilities of 5 events that obey exclusivity relations given by a pentagon, which means that 2 neighbors cannot happen at the same time. If you make a non-contextual model, you never go above 2. With quantum theory, you can go up to square root of 5. And with more general theories that only obey the idea that no 2 together, no connected events will happen in one round, then you go up to 5/2. So those numbers are not simple numbers, are not things that come from nowhere. They are related to the graph, so if you get the same sum of probabilities for a general exclusivity graph, those 3 numbers that will appear here are 3 graph invariants. Those 3 important graph invariants. The first of them, the classical of them, is the independence number. The last one is what's called the fractional packing number, so only respecting exclusivities. And the one that we love is the Lovász number that relates to quantum theory in this graph approach. Okay. Now, non-locality, you are all aware of this. We have different pictures of Alice's and Bob's. And the central model for this 2-part thing of they receiving independent fresh questions, X and Y. Each of them receives an output from their own boxes. And we describe this in this behavior approach of P, A, B, X and Y, given X and Y, with the simplest and still important, very important example, CHSH, when all those things are binaries. So 2 parts, 2 different questions for each part, 2 different answers for each question of each part. And this can be described by this very beautiful inequality that probably is not the way you are most used to, the way it has appeared here many times is this one. But this is the way we like for graph approach. So you can recognize that here you have A0, B0, and this is the probabilistic way of saying A0, B0. The 0, 0 of the questions is here, the X and Y. And here we are adding the situations when they agree. So will become a positive number. Here is add. And the same thing for 0, 1, the same thing for 1, 0, and the opposite thing, because of this minus sign here, for the 1, 1. So in 1, 1, we are adding when they disagree. So this is the central point. And what I will do in the next few slides is to show how this thing can be immediately understood from some colored graph approach. But before the colored one, the black and white that was already known in the original paper, in the 2010 paper. So here we will translate this 8-term inequality in this 8-vertex graph, just recognizing that if we start from whatever, it is a graph transitive thing, so let us take this first thing here. So time for picture. Hello. You have to appear well in the pictures. You see? One again. So 0, 0, it's excludant with these 1, 1 answers for the same questions, 0, 0. And it's also exclusive with these other two things here that we recognize here in the bottom part to be, in this case, the same question 0 with the answer 1. This is excludant with this. And in the other case here, the second question will be 0 with answer 1. So that's why, you see, hello. But those two guys are the ones that appear here, and we can complete this whole pizza and just pay attention that this center here is not a vertex. It's just a crossing of many edges. So it's an 8-vertex graph. Okay. And the most important part was where this 3 comes from, where we can recognize this number 3 in this graph. Those 3 green balls that are just spread in a way that you can never have 2 balls connected by an edge. So you choose vertices. This is the definition of independence number. You have to discover in the graph which is the largest set of vertices where no 2 vertices can be connected. And this is the way of doing this for this kind of graph. So you can try, and you never will succeed in having more than 3. And this is one configuration of those 3. Okay, so where the colors come, the central idea is that this is not only a non-contextual inequality, but this is a Bell inequality. You have parts in this. You have different reasons for having exclusivities. You can have exclusivities that come from one part or from the other part, from Alice or from Bob. And this is what we here draw. So it's the same vertices. You have the same exclusivities. And remember that I start here from 0, 0 for 0, 0. And the opposite one, you have the same 2 questions with opposite answers for both. And that's why we have drawn here 2 edges, one in blue, one in red. The idea is that you have a red edge for Alice, a blue edge for Bob, and here for these other situations is different. Here you can only have a red edge, and this comes from this term here, because you have the same question for Alice with a different answer, and this is why you have this exclusivity here. And you continue the process, recognizing where you have blue, where you have red edges, and just obtain these more interesting 2-color pizza. So, even more interesting than seeing this in this way, or not more interesting, but you can split this pizza in those other things here that we can recognize in the following way. So if we start here from 1 and we say, now I will play the role of Alice, so I only can see red edges, and I walk by them. So go from 1 to 2, then from 2 to 6, 5, and back to 1. This is what this square here mean. And you see that the other 4 vertices obey a similar red paths. You can start, for example, from 8 and come back to 7, then 3, 4, and back to 8. This is this guy here down. Okay? Analogously for blue, you have here blue, 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 blue. And you can recognize those 4 guys here in red all are related to one and the same question for Alice. That in this labeling is 0, but the labeling is not the most important part. The labeling can come a posteriori, and here you only see that 1 have to be exclusive for Alice to 2 and 5, and that's what you have here. The question 0 for Alice has 1 answer for 1, opposite answers for 2 and 5. And since it's dichotomic, those 2 have the same answers, is why they are not linked. You have a square and not something with more edges. And 6 has the same answer as 1. So 6 here, you have again this question 0 for Alice with answer 0 for Alice. Okay? And you continue with all this way. And the interesting point in this is that now you can essentially forget about writing the inequality. It's already written here in this colored graph, because you know that you have 2 pieces of red, so you have 2 questions, that you only need 2 different answers for labeling all the exclusivities, so you have 2 dichotomic questions. Here, the same for blue, and since we can recognize here that each event is related to jointly these and that, so you now know that this event here is 0, 0 questions with 0, 0 answers, so the same thing here, and continue writing the sum of all of them has to be smaller or equal to the independence number. That's again 3. So all the inequalities encoded in the graph. That's the point that I'm stressing in this slide. And then we can go through other interesting inequalities. So this is the first example of what was called Pentagonal Bell inequalities. Pentagonal because they were born from pentagons. They start from graph approach. But the interesting point is that to that moment they were considered 3 different pentagonal Bell inequalities. This is the first one. That's why IP1, pentagonal 1. And its graph representation is this one. Its colored graph representation is this one. One of the interesting points is that we have here numbers 1, 2, 3, 4, 5, and you can recognize this pentagonal Bell inequality inside this CHSH graph. You simply forget about 6, 7, and 8. So since you forget about this, there is no double edge here for 2, 3, and 4 anymore. But you have this double 1, 5. This is what is depicted here. And you simply alternate red, blue from 1 to 5. So this is essentially induced in this scenario here. So you can simply write, as it's written here, as 5 of the 8 terms of the usual CHSH inequality. This gives you the Bell pentagonal inequality, which has local bound 2, that's the independence number of the pentagon, and quantum mechanically it can go up to 2.178, and we'll come back to this number soon. The other 2 Bell pentagonal inequalities were written like this, but the interesting point is that they have essentially the same colored pentagon. So what has changed from the previous slide to this one? This double here has disappeared. You now only have blue connection in this part, so in the sense this is the simplest 2-colored pentagon. All the edges are simple edges. You have no double edge anymore. And you can see that for Bob, this is what you have. For the blue part, you have 1 simple edge, and this is 1 question with 2 different answers. And here you have this path of size 2 that you can also associate to one question with two different answers, because those two are not connected, so they are not exclusive. So you can say that for Bob, this is the same question and answer for 1 and 4, and this is what you can see down here. 1 and 4 are those guys here. While 5 has the same question with opposite answer for both of them, okay? And for Alice you have two different choices. So you have one question for this edge with two different answers for vertices 1 and 2, another question for here with two different answers. But here you can choose what you can choose. If you simply say, I will not ask anything, and this is what is written here with this marginal, with this space, or you make one question that essentially has always the same answer. And this is essentially irrelevant. So there is no difference graphically in this concept here from these two, and it's not a surprise that the quantum maximal value that can be achieved for these two inequalities is the same. More examples. I3, you see different and beautiful patterns like these. You can even prepare some t-shirts and sell and things like this. Or the other less symmetric, but at the same time very rich structure that you have many different small pieces, so you can also prepare interesting draws. And this is a work already published with those guys, Adan, Rafael, who is here, Cristiano, and Antonio Lopes Tarida, who was non-locally contributing, and you can see the drawings in the board while this was being done. But the central point in making this is, okay, we have to translate physics to graphs to physics. In this case, physics to colored graphs and colored graphs to physics. And essentially, to understand what we can learn from this. So from physics to graphs, all those examples that I have discussed so far, and when it appeared, it was related specifically to non-locality. So we are always discussing Bell scenarios. So one important question was, how can we recognize from a colored graph if it is related to some Bell scenario or not? If it's a Bell graph or a Bell coloring, as we refer, or not. And this is something that we could understand after some time, that if you have a Bell graph, for each color, we have seen examples, and the examples motivate the idea. Piece is related to one question, and this is central in usual Bell scenarios. You have many different questions, but you do only one at each round. You have to choose among the questions and perform one of them. So this is the central idea, and then start from the simpler situation. If you have one dichotomic question, you can label this thing here with answers 0 and 1. And as we already have studied before, you can also label this path of size 2, giving the same answer for the two extremes. And you can have this square, this disguised square that already appeared in the first example, in the CHSH example. Remember the 4 squares inside the pizza, but you could have more general things like this, but not that general. It's essentially some of them will receive the 0 label, the others will receive the 1 label, and every 0 has to be connected with every 1. This is the central part in only having one dichotomic question. So one dichotomic question has to be translated into one of those things here. Of course, this continues to any bipartite complete graph for each part, for each piece of each part. But life is not complete with dichotomic questions. You can have trichotomic and even more general. But this is what you get, the structure that you get if you have 3 outcomes for the same question. Then each of them is exclusive with the other 2. So you have this triangle, but again, as here you can essentially duplicate this vertex, here you can do the same. And and oh, sorry, the labeling, and then here, if you duplicate, for example, this guy here, you can have this structure. And you can have many, many, many different structures, but with the idea that you have 3 sets of vertices, each vertex of one set connected to every other set, every other vertex of other sets. This is what is called a tripartite complete graph, and this is essentially the structure. You need, if you have a bell-colored graph, each color is divided into connected pieces, and each piece has to be a k-partite complete graph. You can have different values of keys for different pieces, but each piece has to be a k-partite complete graph. Okay, examples. Usually life becomes easier with examples, and I have to run. So those 3 examples of bell coloring, this one with 3 colors. One very interesting thing is that we can recognize here 2 parts, 2 questions for each part, and 2 dichotomic. So this is also in a CHSH scenario. Here we have 3 questions for each part, so 2 parts, 3 questions, dichotomic questions. Here we have 3 parts because we have 3 colors, each of them with 2 questions, binary questions again. And this is non-bell because we can see that this structure is not allowed. And okay, let us go to the other way around, and this is, in a sense, more fresh than the rest. So another interesting question is this. Is it possible to get the maximum violation of basic contextuality structures under L constraints? So let me translate what we mean by basic contextuality structures. And this translation essentially comes from the idea of wholes and anti-wholes. That essentially comes from the perfect graph theorem. So the perfect graph theorem says this fantastic thing that if you get a graph and you see the induced subgraphs, what's an induced subgraph? Choose some vertices and now consider all the edges that are in your original graph. Okay? So choose some vertex in the graph, and you only have to test if among the induced subgraphs you can find odd cycles or their complements. If you can find, bingo, this is not a perfect graph. If it's impossible to find, this is a perfect graph. And one interesting point is that for perfect graphs, those 3 graph invariants that I discussed in the beginning are the same. And if they are the same, it means that you cannot have violation of any non-contextual and non-contextuality inequality that comes from the graph. So this is the reason for odd cycles and odd anticycles being considered as the basic contextuality structures. And this is what we are playing with. So now we want to consider all the bell coloring with 2 colors of cycles. So here some pictures up until 13 vertices of the cycles, the odd cycles of 13 vertices. And the interesting part is that we can see that they will not reach Lovász numerically until 19, so much more than what's drawn here. We have 15, 17, and 19 would appear here down. But another very interesting point is that for those cases that we numerically checked, we also know how to obtain it explicitly. So I did not discuss how we really obtain the Lovász number, but it's completely related to describing measurements and states. And so this is the central point in this situation. And we know how to reach those guys. We have essentially a formula that agrees perfectly with what is only upper bounded numerically with some NEPA-like hierarchy that we can run. And for more than 19 vertices or more colors, we have good reasons to believe that it's also impossible to do, but it's still not complete a good proof for this. Okay, anticycles. So the first interesting anticycle is for n equal to 7, because for n equal to 5, the anticycle is isomorphic to the cycle. So all the discussion for the Pentagon has already been done. But then for 7, I should have waited for showing this here. But the question is it possible to get louvers with this colored louvers? That is the generalization that we proposed before for getting guys at this quantum bound from colored graphs in this case. So this is the central question, if we can reach. And our surprise was that doing some exhaustive search, yes, we can. For this beautiful guy here, that is a complement of C7, it's an anti-hole, in the sense that you can imagine C7 with steps of size 3. You can come from 1 to 4, then 4 to 7, 7 to 3, 3 to 6, to 2 to 5, and then close in 1. This is another way of drawing an heptagon. And the complement is what's depicted here. And this coloring that also essentially separates things in 2 heptagons reaches louvers with the colored louvers. But what's the tricky? It's not bell. It's not in the allowed constructions that we discussed before. You have passes of size larger than, in this case you have a cycle, not a pass, but one way of understanding that you have something larger than a pass of size 3 or a square, and this is not allowed for Bell. This is not a k-partite complete thing. And this guy is the only 2 coloring reaching louvers. The answer for anti-heptagon is okay, it's impossible with Bell colorings. And we can prove that even with more colors, we cannot have louvers with Bell colorings of the anti-heptagon. Okay, so what else we learn? But then we need to go to the other anticycles, and we have not good results for these yet. But another interesting point is for this very charming guy. So remember, we can see again Alice and Bob, and you can see that Alice will have an heptagon for herself, in the same way as Bob has an heptagon for himself. And contextuality people, whenever see an odd cycle, say, okay, this is a contextuality test in itself. So this is a basic contextuality thing. And we love to make questions like, can we get those? Can we have this optimal colored louvers for this structure here, and the maximal violation for those heptagons here? Okay. This is the question, and the interesting answer is essentially yes. What do I mean by essentially yes? That if you want both of the heptagons to be maximally violated, no, then it's too much. But if you are happy, as we are, with having one of the players, say Alice, with her local measurements being good for making louvers with the heptagon, and when making measurements together with Bob, to have the colored louvers for the anti-heptagon, then we can do. But there is a tricky situation. Naturally, this happens for different quantum states. For the second thing, you need entangled states. For the first one, you need pure state for Alice. So it would not be reasonable to expect to have both with the same state, but you can do with the same measurement. So you can do the idea of having 7 boxes that you know compatibility rules for them, and it only depends which state you enter. If only Alice, or an entangled state of Alice and Bob, that together with other 7 boxes for Bob, you can have this anti-hole with this beautiful coloring that is non-Bell. So in a sense, you have to make sequential or joint measurements in each side. It would be a 4 measurement. And now it brings me to the takeaway message, to the last 20 seconds of the time. And colored graph approach brings translate contextuality scenarios that including parts, which includes the Bell idea, but not restricted to it. Very basic questions are still with incomplete answers, and we have to work more on them. We can have this interesting situation of the same measurements allowing you for maximal contextuality, maximal global contextuality, or maximal local contextuality. And Unicamp is a very interesting place to work, so consider going there sometime. And also remember to see tomorrow's talk of Rafael and Roberto's poster in the poster section that is continuous in time if we are not all the time here or eating. So thank you very much.
Questions? Peraí.